Hey everyone, and welcome back to part 4 of this video on pipe flow. In this part, we're going to be going through a worked example. And for that worked example, we're going to use the pipe rig we looked at in part 1. We're going to calculate the theoretical head loss across the entire pipe rig from start to finish. And hopefully the theoretical calculation will match up with the piezometer readings. So let's remind ourselves of what the different components were on the pipe rig. It started with a 15 mil diameter which ran straight for 100 centimeters, right up until a right angle bend. We then had another 50 centimeters followed by another bend. We then had a small 12 centimeter length before an expansion to the 22 mil pipe occurred. It then finished with 60 centimeters of larger pipe diameter until the location of the final piezometer reading. So now that we know the different components, we expect there to be friction losses across the entire 162 centimeters of 15 mil pipe, friction losses across the 60 centimeters of larger pipe diameter, and finally we expect there to be local losses at both bends and the expansion connecting the two different pipe diameters. So let's begin the calculation. The first thing we need to know is the flow going into the pipe rig, as the incurred head loss will depend on that. We measured the flow by simply recording the time it took to discharge 1 liter of water. In this case, it took 13 seconds for 1 liter of discharge to occur, which gives us this flow rate. So now that we have our flow value, the first thing we need to do is determine our friction factor, lambda. It's important to note that for both the pipe diameters, we're really interested in the internal diameter of the pipe. The 15 mil and 22 mil are external diameters, and therefore the wall thickness should be subtracted in each case to represent the actual available area the water can flow in. With our true diameters for both sections, we can now begin by using this simple rule of geometry for a circle to calculate the cross-sectional area of each pipe. And now, using the relationship that flow equals velocity times area rearranged, we can obtain velocities for the water in each of the respective sections. We now have all the variables necessary to calculate two of the axes on our Moody diagram. The first axis we can calculate is our Reynolds number for our flow. It's important to note here the denominator, kinematic viscosity. This will depend both on the fluid in question and the temperature it's flowing at. In this case, we're working with cold tap water. Therefore, 1.4 times 10 to the minus 6 is used. There are many reference books and internet sources available with tabulated values of kinematic viscosity for most of the fluids you'll encounter at a variety of temperatures. The second axis of our Moody diagram we can calculate is that of relative roughness. Similarly here, this depends on this variable E, effective roughness, which is material dependent. Reference books provide effective roughness values for nearly all pipe materials commonly used. In this case, the value for PVC pipes is 0.0015. And we can now input these axes values onto our Moody diagram to obtain a pipe friction factor. We can see here the value for the 15 mil pipe was 0.038, and the value for the 22 mil pipe was 0.042. And we now have all the information we need to calculate our head losses. And we can now use our Darcy-Weibach equation we introduced in the first part to calculate the head loss across the sum of the entire 15 mil diameter pipe length. And then similarly across the wider pipe section. It's important to note significantly less head loss occurs in the wider section. This was to be expected as not only does it refer to less than half the total length, but as the head loss is inversely proportional to the diameter, whose increase in itself caused a reduction in the velocity, which was then squared in the numerator, this chain of connected variables shows how increasing the pipe's diameter can have a dramatic effect on the rate of head loss it incurs. Now that we have our frictional losses, we also have two types of local losses due to the changes in geometry. Firstly, there were two 90-degree bends in the 15 mil section. Again, the 0.5 value for our C for a 90-degree bend is an approximation. And then there was a local loss due to the expansion where the two different pipe diameters met. It's worth noting how much larger the head losses caused by friction are than from local losses. This is why these two are commonly referred to as major and minor losses respectively. And now that we have all our frictional and local head losses for all the different components, we can now simply sum them all together in order to obtain the total head loss across the pipe rig. Naturally, there have been quite a few approximations and simplifications at each stage, so to expect a theoretical result to exactly match is unrealistic. When we look at our piezometer reading, and we can make the clear water columns a bit easier to see here with the addition of some blue lines, we see a total head loss of approximately 16 centimeters, which is relatively close to that which we calculated. This discrepancy is likely due to the use of approximate values combined with some additional head losses which occurred at the connections of the various sections. We also see the small 0.7 centimeter loss across the 22 mil section calculated is the reason why the final readings are also close together. Hopefully, this shows you all the useful tool in the ability to rapidly calculate approximate values of head loss for pipes of different geometries and compositions. If you'd like to now test your own understanding, the pipe rig was actually run a second time, this time with a different flow rate. This time the discharge was 1 liter every 28 seconds. In the description of the video, you can find all the starting data you require to try and do the calculation yourself this time, along with an image of the actual piezometer results so you can compare them to your approximation. Now, I hope this video has been helpful to you, and I'd like to thank everybody for watching.